So let me give you a problem just on your own, okay? And you try and do it, and then we'll do it together, and let's see how you do, all right? I want to find the volume, volume of the solid generated when the region bounded by f of x equals root x. I love this one. Root x, the y-axis, whoops, not the y-axis, I want the x-axis. The y-axis gets really interesting. The x-axis, and x equals 4 is rotated around the y-axis. Now, before you get started, before you try this thing, let's sketch it. Let's see if we know what exactly it is that we're looking at. So here comes f of x, right? This is y equals root x. Here's x equals 4. Hey, this is starting to look a whole lot like the problem that we just dealt with. However, it's a little bit different, isn't it? So, oh, by the way, the x-axis is down here. Now, what are we doing? We are going around the y-axis, aren't we? Okay, now, first things first, let's think about this. If I'm going to go around the y-axis and I'm going to use washers or I'm going to use discs, then what's my action going to look like? Well, let me grab a little slice. I'll grab a big old slice of action. Do you see how that guy right there is your action? It's going to have a width of delta y, and then you're going to have to think about what is this? Well, think about what that is. This is where it gets a little bit tricky. But really the question that you want to ask yourself is there a hole between the action and the axis of rotation? All right, now try it. I'll meet you back here in just a minute. See if you can just set it up. Don't even worry about integrating it, okay? Don't even worry about integrating it. Just try and set that sucker up. Okay, so hopefully you gave it a shot. So let's figure out the volume of the ith interval. So what we know is we're going to have some y sub I over here, right? Hopefully we realize that when we bring this sucker around, what we're going to end up with is something kind of like the top half of a bagel, right? That doesn't have a hole in the middle. And then this little slice of action is going to end up over there. Right? Now, I want to make sure that there's no confusion here. I ask you what the width of this is, but we don't really use the width of it, do we? Because we know when we're going to do washers, which this clearly is, if I look at it, right? If I rotate that guy through 360 degrees, I end up with this crazy washer looking thing. It looks like this, got a hole in the middle of it. So I'm going to do pi, right, times the integral. Well, where am I taking where's the action taking place from and to? In other words, where am I bringing these rectangles from and to? This is a great problem because we know this point is at 4, 2, right? We know that the thickness of the action is delta y, so our limits are going to be on y. So rather than integrating from 0 to 4, we're going to integrate from 0 to 2. This is 0 to 2. Then my outside radius. Now let me make sure everybody gets this. Let's go red, obnoxious. My outside radius, right here, this is my big radius, and this is my little radius. So what I do is I take my outside radius and I square it. Well, what is my outside radius? Well, it's 4, right? It's the distance from the y-axis out to this line. So that's going to be 4 squared, outside radius, and then I carve out the middle. Well, what is the middle? All right, let's see. This is a function of y. So y equals root x doesn't work. So I'm going to have to turn this into x equals y squared. We've done that before, right? We did it on the last problem. So my inside radius is y squared, which I square, and then I do dy. Whoops, no, I'm sorry. This is v sub I, so I need to be a little bit more, I need to pay a little more attention. This is delta y, because we're doing the volume of the ith interval, and then that's going to be y sub I. So the overall volume is going to be pi times the integral from 0 to 2 of 4 squared minus y sub I squared delta y. And you guys are probably going to yell at me because I always get this, I start talking about the v sub I, and then I forget that it doesn't need an integral sign because all we're doing is looking for that ith. Okay? So this is the v sub ith, and this is the overall volume. All right? Okay, now, Watch this. I'm going to write a crazy problem, okay? I'm going to find the volume of the solid generated when the region, notice how I'm trying to get you used to this terminology. This region bounded by the x-axis and f of x equals negative x squared, it's a negative x squared, plus 2x is revolved or rotated. When region bounded, rotate. Yeah, I'm going to use them both. Revolved around the y-axis. Now watch what kind of trouble we get into here. All right, so what I want to do is, I'm going to give myself a little space on the left. What I want to do is, I'm going to take the graph of negative x squared plus 2x. If you think about this, this doesn't take a whole lot of work. I can go x times negative x plus 2, and what I end up with is a value, I end up with a quadratic that looks like that. Ooh, that's pretty good, actually. That's not too bad. Now, I'm bounded by the x-axis in the curve, so does everybody see that that's everything in here? Now watch this. You may say, okay, Ripley, I'm good at this. This is a piece of cake. I'm going to go around the y-axis. So what I'm going to do is I'm going to draw myself a little sliver of action. Uh-oh. Wait, what? Hold on. Wait. This is y equals negative x squared plus 2x, which, if you think about it, what's our problem? Guys, this isn't a function of y. It doesn't pass what would be considered the horizontal line test. In other words, when I try to go to find the height of my quote-unquote action, I'm taking the distance from this curve to itself, and it makes no sense. So in terms of being able to use the disk or the washer method, I'm screwed. Now let me say that again. The reason that I'm screwed is because this is not a function of y, which means I can't go around the y-axis. So what we're going to use is we're going to use something called the shell method. And the shell method is so cool, and it's very, very clever. And it's going to be a little confusing at first because your brain's going to be in disk and washer method, and then all of a sudden I'm going to make it change. However, I want to take you to a website, and I want you to look at some graphics of what the shell method really is. But first, let me explain what we're going to do. What we're going to do is we're going to take a slice of action that looks like this. And this is going to be delta x, which is always really helpful, right? Because that helps us set up our limits and all that good stuff. And I'm going to rotate this thing through 360 degrees. So what I end up with is, if you think about it, what I'll end up with is kind of like a tuna fish can that has the top and the bottom cut out of it. Now, have you ever thought of those? They're called Russian nesting dolls. You know how you open up, they look like bowling pins, and when you open them up, there's a smaller one in there, and you open that up, and there's a smaller one in there, and you open them up, and there's a smaller one in there. That's kind of what we're doing. What we're doing is creating a shell, a cylindrical shell, and when I stack a whole bunch of these together,